Hello, my name is Tiago Rodrigues, and I am an assistant professor at the Graduate School of Information Science of Tohoku University. This video is my lecture on nearest neighbors. This lecture belongs to the second part of our pattern recognition course. Initially, this lecture was supposed to be about clustering, but due to a change in plans, we will discuss nearest neighbors instead. I mentioned this last time, but this second part will have 5 lectures, with the last one being reserved for solving Kadai 1. The Kadai 1 will count for half your total grade in this course. You must solve all the problems in the Kadai and send your answers to me by email before the deadline described inside the Kadai file. Your answers can be handwritten or typed, and they can be in any file format. Just make sure to name your file with your student ID, your name, and the name of the course. The Kadai file can be found in the Google Classroom associated with this course. Now, on to our lecture. For today's lecture, we will think of a classifier algorithm for identifying clothes. Imagine an automatic machine where each piece of cloth will pass through. This machine must put each piece of cloth in a different box based on what type of cloth it is. For this problem, we will consider a rather simple situation where there are only 4 possibilities: shirt, t-shirt, vest, and sweater. As input to help in our problem, we will have 4 label elements. Let's call them A, B, C, and D. We know that A is a shirt. We know that B is a t-shirt. We know that C is a vest. And we know that D is a sweater. Given these 4 examples, our goal will be to identify a completely new element and put it in one of those 4 categories. For all elements, knowns and unknowns, we have 2 data: their weight and sleeve length. So we know that A has weight y sub A and sleeve length x sub A. Thus, we have 2 features: weight and sleeve length. Having limited features makes sense, as we do not want to measure and test all possible features of each element. That would be too expensive. Instead, it is always better to work with few features, only the most important features. The most important features are the ones that allow us to differentiate between our categories. The set of known elements will be called our library. So, in this example, our library has the 4 elements: A, B, C, and D. Given all this information, a good idea for classifying new elements is to compare them with the elements we have in our library. Our library has examples of our categories. By comparing an unknown element with our already classified elements in our library, we can check which one is closest and classify them together. The base behind this is that, logically, shirts will usually have similar weight and similar sleeve length. To make our classification easier to visualize, we can put it in a graph. To do this, we will make each feature correspond to one dimension. Since we have 2 dimensions in this example, we will have a 2-dimensional graph. Then, we can graph all elements in our library. Finally, for each new element that we want to classify, we first put them in the graph. Then, we calculate the distance from that new element to each of our library elements and classify the new element with the closest one. What I just described is a classification algorithm called nearest neighbors. So, let's see how this illustration technique works with our example. As mentioned before, each feature is a dimension. Let's start by graphing our known elements. A is a shirt, and it has low weight and long sleeves. B is a t-shirt. Compared to A, it has shorter sleeves and it also weighs less. C is a vest. As a vest, it has no sleeves. It is also heavier than both A and B. Finally, D is a sweater. Its sleeves are as long as A's. It is also heavier than all the other elements. Now, What if we have a new element E we want to classify? First, we measure the weight and sleeve length of E. Then, we graph it accordingly. Now, we can just visually check and say what we think E is. E is closer to B than anything else. Thus, we can say it is probably a t-shirt. The distance in a graph is also called Euclidean distance. It can be easily derived by the formula shown here. The base behind this formula is finding the absolute difference in each dimension, adding these values, and getting the square root of the sum for the overall distance. So, in our problem, we will use the difference in sleeve length and weight in order to calculate the distance between our unknown and the known elements. It may be easier to understand if you see the distance like this. The distance in each dimension plus the Euclidean distance form a right triangle. From here, the Euclidean distance is obtained by the Pythagorean theorem. Based on this Euclidean distance, we can create what is called a Voronoi diagram. A Voronoi diagram divides a graph based on some points called centroids. Here we will use the elements from our library as centroids. Each area in the Voronoi diagram corresponds to a single centroid. All points inside that area are closer to the corresponding centroid than all the other centroids. To create a Voronoi diagram, we take the centroids 2 by 2. For each pair, we draw a divisory between the two centroids that is centered and perpendicular to the distance between the two. This divisory is called the decision boundary because it divides the graph in two, the points closer to one centroid and the points closer to the other. It will be easier to understand from an example. Let's create a Voronoi diagram for our library of clothes. First, let's start with A and B. We begin by drawing a line from A to B. This is the distance from A to B. Then, we draw a line perpendicular to that distance and that cuts right in the middle. This is our decision boundary. All elements to the left of the decision boundary are closer to B. All elements to the right of the decision boundary are closer to A. Now, let's repeat the same process with A and C. First, we draw the line that defines the distance from A to C. Then, at the middle of that distance, we draw a decision boundary perpendicular to it. Finally, let's repeat the process for A and D. First, we draw a line from A to D. Then, as before, we draw a decision boundary, cutting that line in the middle. Now we have all the decision boundaries that involve A. Note that when we draw all those boundaries together, A is located in an area of its own. This would be this green area. By our definition of decision boundaries, we can conclude that all points inside this green area are closer to A than the other centroids. Any point outside the area will be closer to one of the other centroids, since it will be on the other side of at least one of the decision boundaries. From here, we repeat the same steps for each of the other centroids. In the end, we will have a diagram that looks like this. Each color corresponds to points that are closer to one of the centroids. All points in the purple area are closer to B. All points in the blue area are closer to C. And all points in the orange area are closer to D. Now, we can classify new elements by putting them in this diagram and checking which area they fall into. A fundamental problem in our example is how we have one representative from each category only. This is highly vulnerable to bias. If, for example, A is a very heavy shirt, our algorithm will expect all shirts to be heavy and have a similar weight to A. When we are then presented to a light shirt, our algorithm will probably classify it as a t-shirt. Or, if we have to classify a light sweater, we might also mistake it as a shirt. Thus, having a small library can lead to an inaccurate algorithm. To address this, we can instead utilize multiple different shirts to base our centroid. This can be done by taking the average of their features. By taking the average, we can lower the impact of the bias in our algorithm. For example, While it is possible that one of the shirts in our library is very heavy, it is very unlikely that all of them will be that heavy. Thus, the average of our library should be closer to the actual average of all possible shirts. From this, you can see that the more elements we have in our library, the more accurate our algorithm will be. Of course, this comes with the cost of extra complexity of having a bigger library and calculating the average from it. To illustrate, let's say that instead of a single shirt A, we have 10 shirts in our library. From this set of shirts, we want to derive a single centroid. This can be done by calculating the average of each feature. In this case, the average weight will be 257.09 grams, and the average sleeve length will be 65.35 centimeters. Note how different this centroid is from taking just A8 or A1 as centroids. We want to decrease the bias from outliers in our library. So, for this scenario, with multiple shirts in our library, taking an average is the most appropriate approach for raising accuracy. If we graph all those points from the dataset, we can clearly see how there is variation across the features. This happens all the time. Even if elements belong to the same category, they are almost never identical. Thus, this is why we use an average across all known elements in these scenarios. By using average, we can get a better idea of what the definition of shirt should be. This also helps us reduce the impact of outliers, which are elements that belong to the category, but at the same time have very different features. For example, A8 is a big outlier. You can see in this graph how the shirts all cluster around our average. Choosing the average is better than choosing a single element exactly because of outliers. If we chose a single element as centroid, we have a higher risk of choosing an outlier. For example, if we chose A8 as our centroid, our definition of shirt would be heavier than the average. This new definition means that A2, A3, and A7 are now incorrectly categorized as t-shirts. If we choose the average as our centroid, we have a more accurate algorithm. Notice how the outlier is still classified wrong. This once again shows how much of an outlier 88 is, and also how it is difficult to achieve 100% accuracy in pattern recognition. Most situations will have outliers that will be misclassified. The objective is to be as accurate as possible and as accurate as it is needed. In summary, in nearest neighbors, we have as input both a library of known elements divided into different categories and a set of unknown elements that we want to put in those categories. To do this, we first calculate one centroid for each category based on our library. Then, from here, we have two options. We can create an actual graph and make a Voronoi diagram in that graph of all the categories. Then we can put the unknown elements inside our graph and identify them according to the areas they fall on. Alternatively, we can just calculate the distance of each element to each centroid and select the category with the closest centroid. The end result will be the same. This concludes our lecture on nearest neighbors. After seeing this presentation, you should be able to complete the second question of Kadai 1. I recommend you work on it as soon as you can. If you have any questions, please send me a message. If not, see you on the next lecture.